What's negative 8 plus a 0? Negative what? Alright, cool. You're an expert. Those are the 4 scenarios. Factor, common denominators, conjugates, expansion. And you can cover them all. Hey, before I do that quick lesson on 2.4, I want to tie in the very first problem I did. So you'll see this at the beginning of that last video. You know what we were trying to do? Remember we just kept getting the slope yesterday? It was kind of tedious. We did from 2 to 2.5. Then we found the slope between 2 and 2.1. Then we found the slope between 2 and 2.01, remember? So in reality, you know what we were trying to do? We were trying to estimate the slope as x approached what number? 2. So we got closer and closer to 2. So I want to write that on the board. So this is funny. The problem we were doing, this is how I wanted to end the 2.3 lesson. You go what? I'm going to take the problem that we did from 2.1. It was number, oh gosh, I forget. Was it number 5?
Sounds right.
Alright, and I'll write the question. This is really what we were trying to do. We were trying to estimate what was going on with the limit of all the slopes as you approach the value of 2. Okay? Yeah, so you'll see this, Colin, you see this at the beginning of that video. We were trying to just do this, and we're like, okay, we just kept playing around with this thing. Well, what's the formula for slope? Y sub 2 minus what? Y sub 1 over x sub 2 minus x sub 1, right? Alright. So we're trying to do that for f of x minus f of 2 all over x minus 2. You know? Y sub 2 minus y sub 1 over x sub 2 minus x sub 1. This is what we're doing. By the way, in the book, he used t's. I'm just changing t to an x. Is everyone okay with that? In the book, he used t's. Now, this was the function. I do have this memorized. I remember this from yesterday. You probably remember. This was the function. 40x minus x squared. No, minus 16x squared. It just had t's. T for time. So if you want to make these t's, you can. I just don't want the t's to look like pluses. So that was the function. But what we were trying to do is find the limit as x approached 2 of those slopes, right? What's going on with those slopes? So this is what we're doing. Well, I just want us to look at this problem now. All right. What was f of x? So what? The only thing is, can you help me out? What is f of 2? All right, so is it 16? I mean, we just have to plug in a 2 here to figure out what f of 2 is, and we're getting 16. 40 times 2 is 80. Minus 16 times 4 is 64. It's 16, right? So this is what we were trying to do. There's your slope formula. We're trying to find the limit as x approaches 2 of the slopes. 40x minus 16x squared minus 16. All right. Take a couple minutes. See if you can find that limit. So I'm plugging in right now when I'm getting 0 to 0. Right? So then this is just like number 5 and 2.1, we were trying to estimate the slope. My point is we should get that number we figured out when we estimated it. When we estimate it, we should get that same answer. Well, I plug in 2 over 2, guess what I get? So any suggestions? Here's your list. What do y'all think? You got an idea?
You make, instead of subbing 2 for x, you make it a point that's really close to 2.
Oh, I got you. So he's going back, he's not using algebra, he's not using the limit laws. What he's doing is he's estimating it numerically. That would work. I bet you'd figure out the answer. What he's saying is he's like, what's the number really close to 2?
2.001.
He goes 2.001, 2.001, 2.001, and boy, you're going to have a really good idea what that integer is. And then just go to the closest integer. Heck, that would work. But I'm talking about this. Let's choose one of these things. So any suggestions? Factor. So we're going to try to factor this thing. All right, so let me write this again. Go to the first one. When you factor, I think it's a good idea to the highest power first, right? Is everyone okay with that? In fact, I'll be honest, I can't stand when x squared is negative, so I like to make it positive. So are you okay if I just, this is just me, I don't like that daggone thing being here. negative. So I'm just going to factor out a negative, so what would be in my parentheses? 16x squared minus a what? Is everyone okay with that? It just makes it easy to factor. Now, can I factor anything else out of the top? They're all even. Does 16 go into 40? Not perfectly, but 2 does. Does 8? Let's factor out an 8. I'll make this problem easier to factor. Negative 8. So we're factoring away, everyone. 2x squared, what would be here?
5.
Minus 5x plus 2. The only problem is, do y'all know how to factor that, dude? Can you factor this guy right here? What do y'all think? Almost done. Oh, we're gonna get this answer. X approaches 2. There's a negative 8 still sitting there. Don't trash that negative 8 though. It didn't cancel. Alright. What's this factor? I bet you one of them's an x minus 2. You all agree? Who's the other one? 2x minus 1. Although you can check it, FOIL it out. So what cancels? Now what do you do with this 2? Alright, what's negative 8 times 4 minus 1? Is this what we got last time? We sure did. Remember? I'll put the feet per second. Do you remember this? We estimated the instantaneous rate of change. Well, that's the exact instantaneous rate of change if this represents position. So this was height. That's the exact velocity at time equal to 2. Isn't that cool? Welcome to calc. That's what's neat about this stuff. We're building on this concept. We don't have to do this old little like plug-in number near it. We're getting more precise. We're getting up to here now. And we're really saying, hey, use the limit laws. You can plug this stuff in here. You can algebraic manipulate it and get your answers. Now we know how to evaluate instantaneous velocity from position. Really kind of cool. Sound good? All right. On the rights. That's why I just wanted to tie that in. I thought that'd be cool. All right, 2.4. And what's this title called? The precise definition of a limit. Well, in 2.4, you're like, how do you define a limit? So I'm going to write this down, everyone. This is on page 110. And he writes something like this. If 0 less than or equal to absolute value of x minus a is less than some delta, then f of x minus L is less than epsilon. And when that's delta and that's epsilon in terms of the Greek letters. Delta and epsilon. Alright. And they got more stuff on this. So I want to tell you the page. If you want to read everything else, they say let f be a function defined on some open interval, etc., etc., etc. And we write limits f x approaches a of f of x equal L. This is what's going on. But doesn't this look what? A little confusing? Alright. We won't spend much time on 2.4, it's okay. But I do want to hit at least just one problem to work from this. Alright? That right there, it's actually a delta. It's a Greek letter delta. Feel free to call it D. And that's epsilon, feel free to call it E. But I want to tell you what they're representing. Very, very, very infinitely small values. Someone got that? The delta and that we're saying they're representing this and that. Delta and epsilon. Some mathematicians call these, if you do the problems in this section, they got some proofs. They call them delta-epsilon proofs. Alright? The only thing is, I would go off all day. I'd spend a week on this section with you. If they said in our curriculum, if they said, I want you to spend 6 hours in this section. Well, they allotted me about a half hour. I said, a half hour? And we're going to have to do some math proof? I was like, no. We'll just talk about the definition. Make sure we get the definition down. True, yeah. So, I mean, you can go real heavy in this section if you're going to be in pure mathematics, but absolutely, if they're only putting a half hour, that's as well we're going to spend it with this. So, and there's this proof, but it doesn't make so much sense, does it? So I gotta talk about where's the delta, where's the epsilon. So I'm gonna come back, can I erase this? So you'll see this, and when this is written, this is on page 110. But I wanna show you in terms of where's the f of x, where's the delta, where's the epsilon in the graph. Okay? So, here's the problem I wanted to show you. Alright. They got this. If use the graph. To find, and Joe, that's a delta. Use the graph to find delta. If 0 less than or equal to absolute value of x minus 3 less than delta. Well, I just put a big law here. In this problem, you're going to use the graph to find delta. If 0 is less than this absolute value, there's another way you can say that when the absolute value of x minus 3 is distance between x and 3. That's another way you can say that to yourself. The distance between x and 3 is less than delta. Then they got absolute value of f of x minus 2 is less than 0.5. But they got a picture of a graph. Alright? And in this graph, there's the function f of x. Alright. Here's the x value 3. I won't even put the 1 and 2 down. There's the y value 2. So let's see how 3 is lined up with 2. By the way, everyone, if this is f of x, I think you all know what's the limit as x approaches 3? 2. Yeah. So you all see this? You all see that, right? But we're just talking about this precise definition here. This is 3 and that's 2. They want us to talk about this funny thing, delta. Alright, so now what else do they have in this image? They showed this. Over here, at x equal to 2.6, they told us, so they gave us little tidbits about this function. At x equal to 2.6, the y value is 1.5. And at x equal to 3.8, way over here, the y value is 2.5. All right. Make this look a little better there, because I want this to be exactly, that's a half from there and it's a half from there. Ah, that looks better. Nice, there we go. All right. Don't let this problem intimidate you, not at all. We're just looking for this delta, right? Now, I want to point out, where's delta? There's a delta and there's an epsilon. Okay, everyone? Delta is this very, very small distance from this value 3. Delta's down here. So delta could be from here to here, or it could be from here to here. Well, where's this epsilon distance I was talking about before? Epsilon is that distance right there. So can you tell me what they're talking about for that epsilon? What's 2 minus 1.5? 0.5. That's why they put a 0.5 there. So the epsilon distance is over here. From that 2, is that distance epsilon. So from here to here, what's the distance from 2.5 to 2? 0.5, okay. What's the distance from 2 to 1.5? 1.5. So there's your epsilon distance, but your distance from 3 to a 2.6, or 3 to the 3.8, is referring to this delta expression, okay? So here's the only thing we got to figure out for this math problem. For our answer for this delta, are we going to use, everyone, what's 3 minus 2.6? 3 minus 2.6 is 0.4. What is 3.8 minus 3? 0.8. The question is, which one of these two answers are we putting for our answer, according to this math proof? All right? We got to figure that out. We got to all logically figure out, are we going to use 0.4 as our answer? Use the graph to find the value of delta, such that this would be a true statement. Brilliant. She knows. She knows. She goes, it's this guy. This is our answer. We're going to use, by the way, in any problem like this, I can make 100 in a row. You always use the smaller of the two radii. Now I'm talking about radii, like distance from here to here. If these are your two values that we're trying to figure out our delta, you always use the smaller of the two in terms of the distance. And 3 minus 2.6 is smaller than a what? 3.8 minus 3. It doesn't matter which way you subtract, you can just do absolute value. Do you want to know why? She saw this. Very good. She saw this. This is 0.4. We're using that because I mean, look what happens here. This is 0.8 away. If you went 0.8 away this way, what would you get to? What's 3 minus 0.8? I'm going to write it down. You get a 2.2 here. And I want you to see where that hits the graph. This x-ray of 2.2 hits the graph right here, right? Which puts you here. Are you still within a half from 2? Are you still within a half from 2? Can you all see it? No, you went over that half distance. This statement, for it to be true, always had to make sure this was less than what? Less than a half. But, if we use the what? If we use 0.4, so we're going to cross that out. Sorry about that. You're not it. Let's use 0.4. Okay, if you go this far, how far are you away? 0.5. Now go 0.4 this way. What would you go to? 3.4. Go up here. Are you within a half distance? Yeah, we're still within a half, aren't we? It says less than. We're still in there. So hey, moral of the story, keep this simple. I could give you 99 more of those in a row. And you're looking for the delta, which one are you always going to choose? The what? The smaller, the closer one.
But where'd you get the 2.6 and the 3.8?
They were given, great question. They were given in the problem. And that's the one problem I like to focus on. It's this idea of what they're going with this precise definition. I mean, we can get in the math proof and stuff is they're saying, the idea of limits is, if you keep doing what? If you keep shrinking this distance, what happens to this distance? I mean, what happens? Like, this is 0.4, but what if I went closer? If you went closer to a point closer to 3, what happens? Up here. I'll get this out of the way. Here, get these out of the way. And when right now,